All right, lesson 216, single phase transformers, dual voltage, fault current code calculation. We're going to focus on some more transformer calculations. We talked about dual voltage secondary. This time I want to get into dual voltage primary and secondary. I don't think there's really a whole lot of new concepts. We sort of cement some old concepts from the previous lesson in here. So right away, dual voltage transformer, we have a dual primary and a dual secondary, meaning we have two windings or two coils on the primary and on the secondary. One coil here, H1 and H2, another coil for H3 and 4, and then the same scenario on the secondary side, okay? So what does this mean? Well, I think our book is going to give us some good examples we'll run through, but I want to revisit some rules for series and parallel circuits, if you remember from year one, because the same thing's going to apply for our transformer coil connections too. So anytime we connect anything in parallel, we remember our voltage rule is E total equals E1 equals E2 equals E3. It's equal anywhere throughout the circuit. Voltage stays the same. The same thing will be said for our, if we connect in parallel our windings, the voltage will remain the same, and we'll visit that here in an example. If we talk about amperage on a parallel circuit, I total equals I1 plus I2 plus I3. It's additive. Amperage adds. Again, no difference with a transformer coil. Same thing on a series circuit, except we're going to be the opposite. So our voltage total is equal to E1 plus E2 plus E3. Our voltage adds. And then our amperage is going to be equal anywhere throughout the circuit. Okay, so we'll remember that. Keep that in the back of your mind as we go to these first couple examples here. And when we're connecting coils in parallel, this is what it's going to look like. Again, no surprise, we have parallel connections here. We're actually going to see it viewed like this more often because usually you're going to see the coils laid out side by side. But it's the exact same thing. So we have our X1 is connected to X3, X1 to X3. We have our X2 connected to X4, X2, and 4. Then we actually have our line sides on X1 and X4. So here we go, X1. Now over here they connected to X2, but it doesn't matter because it's the same point. So these are equivalent schematics here. And then if we're actually looking at a transformer, you're going to see something more like this. Now they did this with the H side rather than the X side. Doesn't matter, primary versus secondary. The theory is exactly the same. So if we're actually connecting in a transformer, you might expect to see something more like this. Looking at that in a series connection, here we have these two coils connected in series. Not a real big mystery there. It's actually laid out pretty user-friendly to begin with here. And then looking at a transformer, that's the way you're going to actually see it out in the field. Once again, they use H's in this example, X's here. Same thing, same concept, just primary versus secondary. So we're going to look at an example here. This I think is the first one in your reading. So we have a transformer with a 120/240 primary, 24/48 secondary. So that means depending how we connect these coils, it's going to depend what voltage we get out of it and what voltage it can receive into it. So in a nutshell, as simply as we can put this, if the lower of the two voltages is desired, so if we're looking at the primary side, if we are feeding this with 120, we're going to connect in parallel, right? Because the voltages in parallel stay the same. So if we have, essentially now we're going to have each of these coils is rated 120 and 120. Connect them in parallel, we stay 120, right? Same with our secondary side. Each of these coils is rated 24 volts. If we want 24 out, we'll connect them in parallel. 24 equals 24. It stays the same in parallel. If the higher voltage is desired, we connect the coils in series. So if we want 240 on the primary side, we'll connect this 120 coil in series with this 120 coil. They add 120 plus 120 gives you 240. Same theory on the secondary side. So in a nutshell, this is probably the most important slide of the lesson. If you can remember that and get that through your head, I think you'll have pretty good success understanding this here. So let's just look at some examples here. So in the first case, we're feeding it with 480. We want 48 volts out. So what have they done? Remember, it's actually now a 240 480 example. So we have 240/480 primary, 24/48 secondary. So if we feed with 480, 480 is the higher of the two voltages. So we look here, we're connected in series, right? It's one path of current through, so 240 plus 240 is going to add to 480. We want 48 out. So we're going to connect 24 in series with this 24, and we get 48 out, right? 24 adds 48. The next version of this, we are still feeding it with 480, so our primary is still connected in series, so the 240 adds to 240. For the secondary, we only want 24, so they've now connected these two in parallel. So voltage is equal, so the 24 stays equal to the other 24. Now the important thing to remember is your current actually now is going to add in a parallel circuit, right? So we would never use this transformer and only connect this load to one coil and leave this other coil hanging. We would get the right voltage, no doubt, but the kVA rating of this transformer would be cut in half, okay? Because on a parallel circuit, remember, our amperage adds. kVA is volts times amps, right? So if we have half the amount of coils or half the amount of amps, we're going to have, a fraction of our kVA as well. So we're always going to use both coils. Again, connecting in parallel, we keep that same lower voltage, right? So next example, feeding with 240, we want 48 out. So if these are both 240 rated coils, we're going to connect them in parallel. 240 in, parallel equals parallel. Voltage equals voltage in a parallel circuit. So we're going to connect the primary in parallel. For the secondary side, we want 48. So once again, just like the first example, we're going to connect these two in series. 24 plus 24 is going to give you 48. And then lastly, the final one here, 240 feeding, 24 output. We have both parallel. So 240, we're going to feed this element, which is 240. This one's 240. Connect them in parallel. They stay the same. Amperage adds, again, same as we talked about. And then same thing on the secondary side with 24. We're connected in parallel. So, it really is that simple, just understanding the difference between a parallel and series connection and what relationship your voltage has there, right? But let's look at the next example. We're going to actually get some math involved here. And this is a good example from your book. It to me, feels like a real life example, something you might actually encounter. So this transformer we're going to deal with, we're only worried about the secondary. They don't talk about the primary here. Not terribly important. It's the same process either way. So we're only looking at the secondary here, okay? So it's a 120, 240 volt secondary, 25 kV. Again, everything's still single phase. We haven't hit the three-phase section of this yet. So that's the transformer we're dealing with. Again, it's a dual voltage secondary, we're going to assume. So first thing we want to do, and if we read through the book, we're going to actually feed a 120, 240 panel with this transformer. So the first thing we want to do, let's put a jumper between X2 and X3 to connect each of these, because remember, each one is a 120 coil. We have 120, we have 120. Connect them in series, they add to be 240. So we connect our L1 and L2 wires, or our actual wires going out to our panel, to X4 and X1 over here. So again, that will give us 240 between the two. One last thing we have to do, since we're feeding a panel, it's a 120/240. If you remember back to lesson 215, we're going to pull a neutral sort of off this center tap, or this X3, X2 connection. That's our neutral point. That's the point between the two coils. If you think back in a series circuit, if we have two equally rated elements, our voltage is actually 0 at this point. Same exact theory here. That is our neutral point, right? So if we take a volt rating, we would then get 240 volts between the black and the red leg. We get 120 between the black and white and the red and white. That's essentially the transformer that feeds everybody's house, every residence, for the most part. There's your 120, 240 transformer. That is exactly what we're dealing with. Okay, so they're going to come in here and tell us, we should mention that each coil can carry half of the rated kVA. So we have half the rated kVA on each winding, because remember, we connect these in series. We're going to have the same amperage flowing through, right? So let's look at here. So if we have 25 kVA feeding this guy, we first have to break that down to volt amps rather than kVA. So let's divide that, multiply that by 1,000, we get 25,000 volt amps. We're going to divide that by 2, because half is in either coil. So 25,000 divided by 2 is 12,500 volt amps per coil. Okay, let's find out what the amperage is there. So by Ohm's law, we can divide volt amps by volts to give us 104.167 amps on either coil. So each coil can carry 104.167 amps. Okay, so that's going to be our max, our cutoff. We need to be aware of that. So let's kind of file that number away for later. So we have 104.167 amps max per phase. So the first thing they do, they throw a couple loads on this circuit here. They tell us circuit 3 is a 120 volt load, 25 amps. Circuit 4 is a 120 volt load, 30 amps. Let's quickly revisit how a panel is connected. Remember, circuit 3 and 4, we look here, they're both connected to phase B if we look at that, right? So, as they've shown here, both of these loads, 3 and 4, are on winding B. So they're both on the same phase, okay? So if we have 30 amps and 25 amps, we add them up, we have 55 amps right now on B phase. So far, nothing on A phase. So let's kind of keep track. So next thing they do is they put a 240 volt load in here. Circuit 6 and 8 is a 240 volt load, 40 amps. Again, if we look at how this panel is connected, circuit 6 and 8, 6 is on the A phase, 8 is on B phase. So 6 and 8, 240 volts, we have to put 40 amps on both phases, right? So remember, amperage is going to be equal. So we need to put that same amperage on both phases. 40 amps flows through both coils. We add that in there. We now have 40 amps on A phase, 95 on B. So we're getting close to our rated maximum, but we're not there yet. It's a little too close for my comfort, to be honest, but let's play this through and see what happens. We're still technically okay here, right? So now they're going to add circuit 1 is a 120 volt 35 amp load, and circuit 2 is a 120 43 amp load. I'm not going to go back to the graphic, but those are both on A phase. So here we are, we put them in there, right? So if we add those up, that's 70 amp total, or 78 total. Add that into our original 40, we now have 118 amps on A phase. That's an issue. We've overloaded this 25 kVA transformer, or at least the A phase coil anyway. So what's the next step? The book goes through this whole discussion. You can tell the guy he's got to get rid of some load, or more realistically, we need a bigger transformer. How do we determine that? Well, the key is, which coil is higher. Well, of course, your A coil is higher. We need a transformer that can handle at least 118 amps. Now, remember, they rate your transformers in kVA, not amps. So we're going to have to break that down and turn that into kVA. So this is a 240 volt transformer we're looking for. 118 amps times 240 volts to give us our VA, 28,320. Turn that into volt amps, we can divide by 1,000. That's 28.32 kVA. So we need a transformer that's at least 28.32 kVA. They tell you in your book, you can check Annex B, the back of your student manual. That gives you some standardized transformer information. If you check that, you'll find the next standard size from 25 kVA is actually 37.5 kVA. So that's the transformer we're going to have to select. So we can actually take this sort of one step further and find out how many amps is that actually going to give us on each phase. So let's first go from kVA back to VA, volt amps. We're going to divide by 240. That tells us 156.25 amps, right, on either phase. So we've actually given this guy a little bit of spare capacity now. Rather than just 118 amps, he's now 156. That's pretty much the range where we want to be. So again, that's, I think, a nice little exercise. The biggest key I can tell you guys is, let's go back to that slide. This is the best slide you need to worry about here in the whole presentation. If you can get this in your mind, you'll have it all. Way back. So, right, if we're looking at this transformer, if we want the lower of the two voltages, we're going to connect that particular side in parallel. If you want the higher of the two voltages, connect that side in series. Like I said, not to oversimplify, but that, I think, is the most important thing out of the lesson here. So again, hopefully you didn't see too many new ideas, but rather we concreted some old ideas. If you felt good about 215, hopefully this was a refresher. If you needed some help. Hopefully this was a little bit of a brush up. Transformers is not going away. We're going to build on this stuff, so make sure we're comfortable and we can go from there.